Hello everyone, my name is Richard Rajan and I'm also working with Kevin Goup and John Deal on this presentation. This week's topic will cover the Heartbleed bug, which was discovered back in April 2014. Some of you may remember hearing about this in the news when Heartbleed was first discovered. It was in the headlines to alert people that there was a vulnerability. Before we discuss Heartbleed, we think it's important to discuss the TLS protocol and OpenSSL to lay a foundation for Heartbleed so that you'll have a better understanding of it. So what is TLS? TLS stands for Transport Layer Security, and in parentheses there you'll see protocol because it is a protocol which is used to secure communication between web browsers and servers. TLS is also the successor to the SSL protocol, which is similar to TLS. SSL stands for Secure Sockets Layer, in case you didn't know. TLS allows privacy protection for user information transferred over the internet. This is possible because of cryptography, specifically symmetric cryptography, which is used to encrypt the data that's transferred. Once data is encrypted, it's protected. TLS also serves as the industrial standard for security. Now, touching back on SSL, in case you were wondering what some of the differences are, TLS supports message authentication, cipher suites, and the key material generation associated with them. TLS also continues to support newer and more secure algorithms, while SSL does not. So how does TLS work? TLS is composed of TLS record protocol and the TLS handshake protocol. The record protocol provides connection security, whereas the handshake protocol allows the server and client to authenticate. It also exchanges keys and algorithms before any data is exchanged. A great example of this Pace's Blackboard website, which happens to use TLS. You can tell our Blackboard site is using TLS in two ways. The first is the address line, where you will see that HTTP is replaced with HTTPS, which shows that it's secured. The second way to tell is the padlock symbol, which in this example is right next to the address bar. In some older browsers, this might be shown on the bottom right corner. However, in recent browser updates, like in Firefox for example, they're both listed at the top. Other than the Blackboard site, chances are you've probably seen this elsewhere, such as banking sites or social media platforms, which shows you that your access is secured. Public key is used to encrypt a symmetric key, and this is usually done by the browser. One computer creates a symmetric key and sends it to the other using the public key encryption. Following this, the computers then communicate using the symmetric key encryption. Once the session is over, the keys are discarded and the process repeats itself every time the communication needs to be opened. Here's the implementation and some of the errors that have occurred with TLS. Now, generally speaking, TLS is when TLS is implemented correctly, it's very secure. Otherwise, it wouldn't be the industry standard. But there have been times where errors have occurred, and this has caused other vulnerabilities and flaws. Examples of this are Cloudbleed, where unauthorized third parties were allowed to read data and program memory running on servers. Another example is the Berserk attack, where man-in-the-middle attacks were allowed because of incomplete decoding of public key signatures. And of course, there's Heartbleed, where OpenSSL was vulnerable because private keys from servers were able to get stolen by attackers. So that brings up the next question. What is OpenSSL? It's widely used software which allows computers to communicate using SSL encryption standards. OpenSSL is incorporated into software packages such as Apache. It serves as a toolkit for the TLS and SSL protocols. secures communication against eavesdropping as well. OpenSSL has the ability to verify and extract certificate information, and it's also a great way to check expiration on a certificate. It also supports many different types of algorithms. Examples of this include AES, Diffie-Hellman, MD5, SHA1 and 2. So how is OpenSSL related to Heartbleed? So the vulnerability actually lies within the TLS Heartbeat extension. Kevin will explain the heartbeat in greater detail, but what it does is it keeps the connection alive. So what you see right below this is a very small line of code. A small line of code actually causes the issue. To elaborate here, memcpy is a command that copies data, and it has 3 other variables which are also needed. You see them there in parentheses. BP, which is referencing a location on the server computer, P1, where the actual heartbeat data is sent to, and then the payload, which says how large the P1 variable is. So when data from, just to give you an explanation of how this line of code works, when data from P1 gets placed into BP, it covers up the old data that was in BP, which is told earlier how large it is by the payload. In a perfect world, this works great until the payload gives a number that isn't true. And this is where the issue actually comes in. memcpy will tell the BP variable that the size is 32 kilobytes, which may already have data from a previous session, because the P1 variable is actually 0 kilobytes. This is following the example that's on the screen there. Our payload says P1 is 32 kilobytes, but it's really 0. And because the P1 variable is actually 0 kilobytes, none of the previous data in BP variable is going to get overwritten, since there's nothing to replace it with. This means that the data sitting in the BP variable will get back to the client. This is risky because it can hold sensitive information such as passwords or credit card information, and this is where the actual issue lies.
Hello, this is Kevin. Now that we understand the security protocol, TLS, and how it's used on the web to encrypt traffic over the net from a server to a client, let's go a little more detail into what a heartbeat is and how folks have decided to use that. Before a heartbeat request was designed in the TLS protocol, is if it would go to sleep, this communication link would be severed and stopped. And that causes a problem because there's quite a bit of information that goes into it to get an encrypted traffic link. So what a heartbeat does is it's an echo function that tells you in a certain amount of bits that the other side is still up and running. So you think about it, if I'm on the server side and I want to know if the client is still there, I send certain bits of information the client's way. And then the client sends their own heartbeat request back, basically mirroring that of the server. And that is what the heartbeat request was designed to do. It was designed to keep the private communication link up and running, so you didn't have to constantly come back and build that private link over and over again. Now what happens when a hacker understood this, they thought there could be a weakness. A heartbeat would have certain information. It would have information on the payload. So what's actually there? And then inside that payload, it would have the size of the information. That way when this information is sent, the heartbeat, when the client comes to it, the client can then match the payload and match the size and send it back to the server. What the server does, stores this information, right? So you think about it. Problem with this link is what hackers realize is like, hey, I can get this information by fooling OpenSSL. That open source code has a flaw. So when the same communication link comes in, let's say I'm a hacker and I'm coming in to hack, right? Here's my hacker. And I'm saying the same type of request before with a heartbeat. But in my size of my data, I'm going to have a payload. Let's just consider that 1 byte. And I'm going to say my size is actually 50,000 bytes. Okay? So typically when that request would come through, it would look like 50,000 bytes would be coming through. And then again, you think about the heartbeat, what it's designed to do is it's designed, once it gets over to the server side, or vice versa, it's designed to duplicate that. So they're going to look for this byte of information, they're going to look here on the chart where it is, and then they're going to go ahead and send it back through another heartbeat request. So the hacker can design a specialized heartbeat request lying on the byte size. So rather than just having one, again, that communication link comes through, here comes my byte, here's my request, I'm going to forward it on, I'm going to look to where it is on my information. They're going to look at this and say, okay, so this is a 50,000 request. So here is that 1 bit of information, and then here is the rest of the 50,000 that we just stole. All this communication, all this information is now been sent back to the hacker. The real issue in design-wise, what OpenSSL should have done is they should have took this, when this request comes in, they should have looked to make sure that information matches this information. But instead, what OpenSSL does is it just tells it does. So rather than verifying that there's actually 50,000 bytes, it's going by what's written here, and that's truly where the mistake lies. Now that we better understand the Heartbleed attack, let's go a little bit more details on the history of the attack.
Hello class, my name is John Paul DiDio, and for my portion of the presentation I'm going to talk specifically about the Heartbleed bug. I'm going to present a brief introduction as to who wrote the code that vulnerability was discovered, who found the code, the flaw, and then I just want to give a very brief example, very simple example of how an attack is carried out. And then I want to introduce some documented attacks, as well as the specific services that are vulnerable and are still vulnerable, unfortunately. And then I'll leave you with some suggestions that companies can take to sort of mitigate any cases of the Heartbleed bug occurring again. As stated earlier, Heartbleed was a vulnerability in OpenSSL software, which is a open source software. And essentially, attackers were able to eavesdrop on network communication and obtain personal information from their victims, such as password, user accounts, or emails, things of that nature. What makes the Heartbleed bug so severe is that it leaves no trace. So for websites to even know that they've been attacked, it was extremely difficult. As word got out that this vulnerability was present, the only thing that websites would do is take preemptive measures and assume that they have been compromised, and they would conduct software patches and updates in order to mitigate any further compromise. The code that was written into OpenSSL was written by a German programmer named Robin Segelman. After writing the code, it was presented to other reviewers, other programmers, and eventually it was deemed efficient and uploaded to the OpenSSL software. However, the Heartbleed flaw was never discovered. Eventually, members of a Google security team and the Finnish security company, I believe it's pronounced Codenomicon, discovered the flaw. Word got back, obviously, to Segelin and Associates, and they proclaimed that this was not intentional because at the time there were a lot of conspiracy theorists, and they thought that the code was written purposely to eavesdrop and spy on certain users. That was never really verified. In this next slide, I'm presenting an example of exploiting the Heartbleed vulnerability. For example, let's just say that a network-connected smart device, such as an appliance, is using OpenSSL software. What will happen is the attacker will send repeated malicious heartbeat requests to the HTTPS server running that smart appliance. Now for instructional purposes, we're going to assume that the appliance is using a vulnerable version of OpenSSL prior to any software patches. So then the attacker is going to attempt to obtain active session tokens for the authenticated user or victim. With those active session tokens, the attacker is now able to hijack multiple user sessions and convince that web server that they're a legitimate authenticated user. Now, somehow, if this is all successful, which we've seen it, the attacker somehow managed to bypass whatever authentication protocols server thought it had in place, as well as any software validation tools without a problem. So that's why this Heartbleed bug was so severe, because even though thought they had everything in place to prevent such occurrences, there was no trace. They had no idea. Attackers were able to carry out something. This is just an example, but this is what they would try to do. Next, I wanted to introduce to you some actual documented attacks that were carried out by exploiting the Heartbleed bug. This case here involved the Canada Revenue Agency. This agency is in charge of administering tax laws for the Canadian government. They noticed that they had a vulnerable version of OpenSSL. Immediately ceased all public online services in order to implement the necessary software patches. However, a bit late in implementing that software patch, and over 900 social insurance numbers were stolen. Again, the method of intrusion was exploiting the Heartbleed bug. Obviously, the most attacks were attempted when Heartbleed was first discovered in 2014. Primarily in April was the worst month. When it was first discovered, there were attacks committed the same day. In particular, on April 15th, 2014, there were reported 300,000 attacks targeting IBM managed security services in that single day. So that certainly puts this attack in perspective. As time went on, obviously, attacks slowed down, word got out, patches were upgraded. However, IBM claims that still half of their affected systems remain unpatched and vulnerable. They reported 7,000 attacks within those managed security services each day. Now, you would wonder, and you would think that, if this happened in 2014 and the severity of this issue has been publicly relayed to users worldwide, you would think that more people would be taking action to prevent this vulnerability. Here in 2017, the website called The Register, which is a European news website, they have reported that to this day, 200,000 services still remain vulnerable to the Heartbleed bug. I just wanted to include this one graphic because it really puts things into perspective here. U.S. services, there's about 42,000 that remain vulnerable. Korea has about over 15,000. China has over 14,000. And there's about over 14,000 exposed services in Germany. So this just puts things into perspective as well. Basically depicts some of the services worldwide that remain still vulnerable to the Heartbleed bug. This is another slide that I wanted to share just to highlight some of the other websites that were affected or possibly affected and the necessary advice they gave their users.